9 minutes is genuinely not enough time to explain what just happened. But we're going to try anyway, because what Voyager 1 has just detected in deep space is something that didn't exist in any physics textbook when this spacecraft was built in the 1970s. It's something that wasn't supposed to be there. It's something that scientists in 2026 are still actively arguing about in brand new peer-reviewed papers published in the Astrophysical Journal this year alone. And what makes this moment different from every single previous discovery in Voyager's 49-year journey is that we are watching the scientific community struggle with these findings in real time, right now, today. Not in hindsight, after decades of consensus has already formed. Today, multiple research teams are using different models and different interpretations of the exact same data, and they are reaching contradictory conclusions about what Voyager 1 has actually encountered. This is not a story about a solved mystery. This is a story about an active mystery still unfolding at the edge of human knowledge. Let's start with location, because in this story, location is literally everything. Voyager 1 launched on September 5th, 1977 from Cape Canaveral, Florida. It flew past Jupiter in March 1979 and Saturn in November 1980, then kept moving outward through the solar system and beyond D. On August 25th, 2012, at 121.7 astronomical units from the Sun, it crossed the heliopause. That's the outermost edge of our Sun's influence, the boundary where the solar wind gives way to the interstellar medium. Voyager 1 became the first human-made object in history to enter interstellar space. Since then, it has kept moving, and right now in 2026, it sits approximately 167 astronomical units from the Sun. That's roughly 25 billion kilometers from home. Let that number sink in for a moment. 25 billion kilometers. The signal traveling at the speed of light takes over 23 hours to reach Earth. By November 18th, 2026, the travel time will reach exactly 24 hours, making Voyager 1 the first human-made object to sit one full light day away from Earth. But here's the specific thing that makes the story of 2026 genuinely different from every previous year of Voyager 1's journey through interstellar space. The region Voyager 1 is currently passing through is not what physicists expected to find out here. And the scientific papers being published right now based on Voyager 1's own measurements are revealing a place whose properties are forcing researchers to revise models they have been using for decades. To understand what Voyager 1 has entered, you need to understand what scientists thought was out here before any spacecraft ever reached it. The interstellar medium, the gas, dust, and plasma that fills the space between stars, was generally modeled as a relatively structured but fairly smooth environment. Yes, scientists knew it had density variations and turbulence. Yes, they knew the Sun's heliosphere would disturb the nearby interstellar medium as it pushed outward against the surrounding galactic material. But the expectation was that once Voyager 1 crossed the heliopause and got some distance away from the solar system's direct influence, it would eventually drift into something close to the undisturbed, pristine interstellar medium. A region where the measurements would stabilize, become predictable, and match the relatively calm picture that remote astronomical observations had built up over decades of studying the interstellar medium from afar. That expectation was based on textbooks. That expectation was based on everything physicists thought they understood about space. That expectation was wrong. What Voyager 1 found on the other side of the heliopause was not a smooth transition into calm, predictable space. It was a layered, dynamic, surprisingly active environment that kept presenting new features as the spacecraft moved deeper through it. Features that required entirely new explanations. Features that are still generating scientific debate. As recently as papers published in April and May 2026, scientists now have a specific name for this region Voyager 1 is traversing. They call it the Very Local Interstellar Medium, sometimes abbreviated as VLISM. That stands for the specific thin shell of interstellar space that immediately surrounds our solar system, distinct from the broader interstellar medium farther away. And the VLISM, it turns out, is a genuinely strange place. It's stranger than anyone predicted. It's active in ways that don't match the models. And Voyager 1 is sending back measurements that are forcing scientists to completely rethink what they thought they knew. For decades, the standard textbook picture of our heliosphere was a smooth comet-like shape with a rounded nose on the side, facing the direction of the sun's motion through the galaxy, and a long, streaming tail stretching out behind it, something like a bubble being blown through water. The heliopause, the outer boundary of this bubble, was assumed to be a relatively sharp, well-defined surface, and the interstellar medium on the other side was assumed to be fairly uniform and undisturbed, at least once you got far enough beyond the boundary for the solar system's influence to fade away completely. Scientists thought they had this figured out. They had decades of remote observations. They had sophisticated models. They had consensus. and then Voyager 1 actually crossed that boundary and started sending back real data from the inside. Voyager 1 has been systematically dismantling this entire picture since the moment it crossed the heliopause in 2012. The first surprise was that the heliopause crossing itself did not look exactly the way models predicted. Instead of a single sharp boundary, Voyager found a transition zone with multiple layers and features. The magnetic field direction did not immediately snap to the expected interstellar orientation. The particle environment changed abruptly, but not always in the ways the most detailed pre-crossing simulations had described. Project scientist Ed Stone, who had worked on the Voyager mission since before its 1977 launch, said at the time that the interstellar space Voyager had entered was not what had been expected. Scientists were detecting shock waves and tsunamis of plasma, phenomena that most people would have thought would be smooth and quiet in the interstellar medium. But the shock waves and tsunamis Voyager was detecting were more common than anyone had predicted. Those surprises continued through the years that followed, and they culminated in a sequence of events between 2020 and 2022 that no model had anticipated. All of it was produced in part by a solar system actively perturbing the space around it in ways that propagated much deeper into the interstellar medium than earlier models had fully captured. But one of the subtler and ultimately very important discoveries from Voyager, one's interstellar journey came not from the dramatic events, but from the quiet background. A persistent plasma hum identified by Stella Koer and colleagues at Cornell University in a 2021 Nature Astronomy paper. By detecting a continuous narrowband electromagnetic emission from the interstellar plasma itself, not triggered by any solar event, but present all the time, the team showed that the VLISM plasma was always oscillating at a measurable frequency, allowing Voyager to sample the plasma density continuously, rather than only during rare shockwave events. The density measurements that came from this discovery showed that the plasma density was not constant. It fluctuated on scales of about 1 astronomical unit, revealing the presence of turbulence in the interstellar medium that was driven not by our Sun, but by the large-scale dynamics of the Milky Way galaxy itself. That turbulence was itself not fully captured by pre-crossing models, adding yet another layer to the emerging picture of the VLISM as a more complex, more dynamic, more physically rich environment than anyone had been able to see from the inside before. Scientists have now identified a distinct sequence of labeled features within the VLISM, each one a named documented event in Voyager's journey. Beginning shortly after the heliopause crossing, Voyager moved through an outer heliosheath region where the interstellar magnetic field was gradually rotating toward the direction IBEX had measured remotely. A compression wave in 2012, driven by a solar outburst that made the interstellar plasma ring like a bell. Then a second plasma wave event in 2013. Then a third larger shock event in 2014 that Voyager was still detecting as it moved hundreds of millions of miles beyond where it started. Then the first pressure front. Then the second pressure front, called PF2, in May 2020 at 149.3 astronomical units, which launched into the magnetic hump that lasted until approximately 2022. And now the post-hump region, the area beyond roughly 155 to 165 astronomical units, whose unusual smoothness and calm behavior is the subject of actively ongoing debate between different research teams using different models and different interpretations of the same underlying data. That is not a transit through empty, featureless space. That is a journey through a structured, layered, scientifically complex environment whose properties at each stage were to varying degrees unexpected. Now, let's talk about the event that has generated the most scientific interest, the most new papers, and the most genuine puzzlement. In May 2020, over a period of about 8 days, when Voyager 1 was at 149.3 astronomical units from the Sun, its magnetometer registered an abrupt jump in magnetic field strength. The field increased by a factor of about 1.35 in a matter of days. The proton density also rose by a similar factor at the same time. Scientists call this event the second pressure front, or PF2. Previous pressure front events had also produced magnetic field jumps. But what followed PF2 was something completely new, something that shocked the scientific community. Instead of the field returning to its previous level after a few months, the way earlier events had behaved, it kept rising. The field strength climbed steadily until it reached a peak of about 0.56 nanotesla in early 2021, then slowly declined to a stable elevated level of around 0.5 nanotesla. This prolonged period of sustained elevated magnetic field strength lasting from approximately 2020.4 to 2022, while Voyager moved from 149 astronomical units out to roughly 155 to 156 astronomical units, was given the name the magnetic hump. The magnetic hump was not something any pre-existing model of the interstellar medium had predicted. It shouldn't exist. It wasn't in any physics textbook. It wasn't in any simulation, but there it was, a persistent, sustained elevation of the magnetic field that defied every expectation. A 2024 paper by Berlage and colleagues estimated that this magnetic hump was caused by elevated solar wind dynamic pressure and high speeds observed at Earth between roughly 2015 and 2017. Compressions driven by solar cycle activity that eventually propagated outward and produced this sustained magnetic enhancement 33 or more astronomical units beyond the heliopause. But the full explanation came in 2026. A major paper by Federico Fraternale, Nikolai Pogorelov, and colleagues at the University of Alabama in Huntsville published in the Astrophysical Journal in April. 2026 used sophisticated magnetohydrodynamic simulations driven by actual solar wind data to model what should have happened at Voyager 1's location. Their simulations convincingly demonstrated that global solar cycle-driven compressions hitting the heliopause can reproduce the magnetic hump observations, and they linked it specifically to solar cycle 24. The same model predicts similar interstellar magnetic field structures will occur once per solar cycle, and that Voyager 1 should experience effects related to solar cycle 25 in the coming years. But here's where it gets strange. Even after the magnetic hump itself faded, something unusual remained. The post-hump region that Voyager 1 has been moving through since approximately 2022 behaves differently from any region of the very local interstellar medium it had been in before. A second major 2026 paper published in the Astrophysical Journal on May 20th by Ju Park, Lang Qian, Daniel Berdyshevsky, Adam Sabo, and Leonard Berlage, covering Voyager 1 magnetic field observations from 2020 through mid-2025, found that the magnetic field environment in this post-hump region remains remarkably distinct from the region upstream of the second pressure front. In the region before PF2, the magnetic field fluctuations were turbulent and non-Gaussian in their statistical character, meaning they varied in ways that deviated noticeably from the smooth, bell curve-shaped statistical distributions that describe random, well-mixed turbulence. After the magnetic hump, that non-Gaussian character essentially disappeared. The field fluctuations became remarkably calm, smooth, and Gaussian. The intermittency, meaning the tendency for the magnetic field to spike and drop unpredictably, in a way characteristic of turbulent non-equilibrium processes, almost vanished entirely. This shift from turbulent intermittent fluctuations to smooth Gaussian behavior is one of the most scientifically puzzling aspects of what Voyager 1 is currently experiencing, because it is not what models of the VLISM generally predicted would happen at this distance from the heliopause. Some researchers initially interpreted it as a sign that Voyager 1 had passed into a genuinely different structural region of the interstellar medium, perhaps crossing into what might eventually be called the undisturbed interstellar medium beyond the zone, shaped by our own heliosphere's influence. This interpretation would mean the heliosphere's reach extends much farther than anyone thought, all the way out to 155 to 165 astronomical units, rather than just the 121.7 where the heliopause boundary was crossed. But the Fraternale and Pogorelov 2026 paper specifically addresses this interpretation, and they argue against it using their detailed numerical simulations. They conclude that neither the turbulence observations nor global models support the conclusion that Voyager 1 entered a fundamentally new region of the VLISM. Instead, their model suggests the smooth, calm, post-hump behavior is a natural consequence of the specific way the magnetic hump event filtered out and dissipated the solar-driven disturbances that had been creating the earlier turbulence, essentially leaving Voyager 1 in a quieter wake behind the passage of that compression event. The hump in their model acted as what they described as an effective filtering boundary, where heliospheric-driven shocks and merged interaction regions weaken or dissipate before reaching the pristine interstellar medium beyond. That distinction matters enormously. If the post-hump smoothness means Voyager 1 has genuinely crossed into truly undisturbed interstellar space, it would imply our heliosphere's influence on the surrounding medium extends even farther than previously thought. If the smoothness is, instead, a temporary artifact of the magnetic hump filtering out disturbances, it implies the medium beyond the hump is still fundamentally the VLISM, just in a temporarily calmer phase that will eventually become turbulent again as the next set of solar-driven compressions from solar cycle 25 arrive. This is the active scientific debate happening right now in 2026. 2 major peer-reviewed papers published this year alone, using the same data, reaching different interpretations. No final answer has been agreed upon. What is agreed upon is that the region Voyager 1 is currently moving through behaves in ways that no physics textbook from before the spacecraft entered interstellar space fully captured, because no physics textbook could have captured them. Until a spacecraft was actually out there making direct measurements, this region simply could not be described with the precision and completeness that observation provides. Now, let's talk about what it actually takes to keep receiving this data, because the engineering reality behind every measurement Voyager 1 sends home from the VLISM is itself one of the most extraordinary stories in the history of space exploration. Voyager 1's main radio transmitter produces about 22 watts of power. That's roughly equivalent to a refrigerator light bulb. That signal, by the time it crosses 25 billion kilometers of interstellar space and arrives at Earth, has lost so much energy that it is billions of times weaker than when it started. The only reason NASA can receive it at all is because of the Deep Space Network, a global system of enormous dish antennas in Goldstone, California, Madrid, Spain, and Canberra, Australia, the largest of which are 70 meters wide and among the most sensitive radio receivers ever built. Even with those massive antennas, the data rate from Voyager 1 is only around 160 bits per second at most. Everything you know about the VLISM, every measurement behind the magnetic hump, the pressure fronts, the plasma density maps, all of it arrived at that trickle of a rate. One thin stream of data crossing 25 billion kilometers of space to land in a desert dish antenna in California, then getting converted into the scientific record that those 2026 Astrophysical Journal papers are now analyzing. The power situation behind that data stream is also worth understanding because it provides the urgency that frames every new measurement. Voyager 1 is powered by 3 radioisotope thermoelectric generators, devices that convert heat from decaying plutonium-238 directly into electricity. These generators have been losing power steadily since launch at a rate of about 4 watts per year. They now produce less than half of what they generated in 1977. To conserve that dwindling power supply, NASA engineers have been making careful decisions about which instruments to keep running and which to shut down. The cosmic ray subsystem was powered off in February 2025. The low-energy charged particles experiment, which had operated for 49 continuous years, was shut down on April 17, 2026. A carefully planned power management operation that the team has nicknamed the Big Bang is being tested on Voyager 2 during the summer of 2026, with the goal of freeing up additional electrical headroom on Voyager 1 if the tests succeed, possibly by no earlier than July 2026 on Voyager 1 itself. If the Big Bang works as intended, it could extend the operational life of the remaining instruments into the 2030s. Those remaining instruments, the plasma wave system and the magnetometer, are the ones generating the post-hump data that the 2026 papers are analyzing right now, and they are not just scientifically valuable in isolation. They are directly supporting NASA's current active mission, IMAP, the Interstellar Mapping and Acceleration Probe, which launched in 2024 and is now operating near Earth at the first Lagrange point. IMAP studies the boundaries of the heliosphere from the inside using energetic neutral atoms, particles that travel inward from the heliosphere's boundaries without being deflected by magnetic fields. But to correctly interpret what IMAP measures, scientists need to know the actual plasma density, magnetic field strength, and turbulence properties of the interstellar medium on the outside of those boundaries. The only source of that information is Voyager 1's direct in situ measurements from inside the VLISM. In this sense, a 49-year-old spacecraft and a brand new 2024 mission are actively working as scientific partners across a distance of 25 billion kilometers, sharing information about opposite sides of the same boundary, one from inside it and one from outside. This partnership also points toward what future missions might eventually build on. The Fraternale and Pogorelov. 2026 paper, in discussing the implications of their simulation results, notes that these results will inform the design of future interstellar probes with improved instruments and more sensitive sensors. No such mission has been approved or funded yet. The proposed interstellar probe concepts that have been studied by NASA would require decades just to reach where Voyager 1 is today. Until they fly, and for the foreseeable future, Voyager 1 remains humanity's only direct scientific instrument operating inside the very local interstellar medium, sending back measurements of a region that was undiscovered territory when it was built, and that is still giving up new surprises nearly half a century into a mission that was only ever supposed to last 4 years. The extraordinary thing about all of this is that the science is happening in real time in 2026, driven by data from a spacecraft that should, by any reasonable engineering expectation, have gone silent years ago. Voyager 1 has now lost 4 of its original 10 science instruments to deliberate power conservation shutdowns, including the cosmic ray subsystem shutdown in February 2025 and the low-energy charged particles experiment shut down on April 17, 2026. Its radioisotope thermoelectric generators are producing less than half the power they generated at launch. A planned high-stakes power management upgrade, nicknamed internally the Big Bang, is being tested on Voyager 2 in mid-2026 with the goal of freeing up enough electrical capacity to keep Voyager 1's remaining 2 instruments alive into the 2030s. Those 2 instruments are the plasma wave system and the magnetometer. Exactly the 2 instruments producing the data that is driving all of these new 2026 papers. And those papers are genuinely important. The VLISM is not just an abstract edge zone that scientists study as a curiosity. It is the region of space that shapes how our heliosphere interacts with the rest of the galaxy. Understanding it properly affects how scientists model everything from cosmic ray shielding, the natural radiation protection our heliosphere provides for the inner solar system, to how the heliosphere generates the energetic neutral atom ribbon detected by IBEX, to how star systems in general interact with their surrounding interstellar environments. Every new measurement from Voyager 1 feeds directly into models used by current missions, including IMAP, the Interstellar Mapping and Acceleration Probe launched in 2024, and now operating near Earth, making the 49-year-old Voyager spacecraft an active current contributor to NASA's present scientific program, rather than simply a heritage mission being nursed along out of sentiment. If you want to follow this story as the post-hump debate is resolved with more data, as the Big Bang power upgrade is tested and eventually attempted on Voyager 1, and as Solar Cycle 25 eventually sends new compression waves out through the heliopause toward Voyager 1's position. Subscribe now because the VLISM is still giving up its secrets one data point at a time. 2026 is already one of the most scientifically productive years this mission has ever had. The magnetic hump was something no model predicted. 2 separate peer-reviewed papers published just this year are still debating what Voyager 1's most recent measurements actually mean. Our own sun's activity can send waves into interstellar space more than 30 astronomical units beyond the heliopause and shape the medium Voyager drifts through there. And a spacecraft launched 49 years ago is still producing data that requires brand new physics papers to explain. That's the story. That's what makes this moment extraordinary. We built a spacecraft to explore the outer planets. We sent it out into space nearly 5 decades ago. We never expected it to still be transmitting. We never expected it to make discoveries this fundamental. We never expected that the greatest mysteries in its journey would still be unfolding today.